So long pending session, we will look at hydrostatic forces that act on submerged surfaces. Surfaces that are submerged in fluids at rest. Submerged in fluids at rest. We will have an organized way of looking at things. How to obtain forces on submerged surfaces. Now, if there is, the simplest case could be, say, a horizontal plane surface. That's the simplest possibility, right? This is a horizontal plane surface, area A, and this is the free surface of a certain liquid, and this surface is parallel to the free surface. This surface is parallel to the free surface. This is a liquid of density rho, and this surface is placed at a depth h below the free surface. This surface, this horizontal surface, is placed at a depth h below the free surface. Now, this is the simplest possible situation. Now, in this case, realize that pressure at all points of this surface is going to be rho gh. That's going to be the pressure at all points of this surface, right? It's a region of uniform pressure intensity. It's a region of uniform pressure intensity, right? The force that will act on this surface, therefore, would be pressure into the area of the surface. Pressure into the area of the surface, which is rho gh into A. That's the simplest possible situation you could conceive of, right? Now, let me next explore when this plane surface is made vertical. When this plane surface is made vertical, okay? So this is ordinary, and you would have all obtained it all by yourself as well, right? Next, look at a vertical plane surface. Next, look at a vertical plane surface. This is the free surface of a fluid, liquid. This is the free surface, let's say, of a liquid of density rho, and this is a vertical plane. This is a vertical plane. And this is a plane surface. Laminar, small uniform thickness, laminar plane surface, whose upper end A is at a depth h1 below the free surface, right? And whose lower end B is at a depth h2 below the free surface of a liquid of uniform density rho. Okay. Now, let me call it PQ because A I am going to use for area. So let me call this PQ instead. Okay. Now, when you observe this surface from this direction, when you observe this surface in this direction, you can only see the thickness of this plane surface, right? It's laminar, uniform, thin surface, right? But when you see this surface from here, what you see is, when you see from here, what you see is, say, an entity like this. Yes or no? This is what you see. When you see from here, you see a planar entity like this, whose thickness is shown in this view, whose thickness is shown in this view. Okay. Now, I want to calculate the force on the surface. I want to be able to calculate the force on the surface. What I do is, at a depth h from the free surface, at a depth h from this free surface, I select a small element. I select a small element here. That means when you see this small element, if you see the small element from here, you see an area dA. You see an area dA. Yes or no? This is the area dA. This is the area dA that you see for this small element at a depth h. At a depth h, from this side if you see, you'll see a strip of area dA, right? And all points on this dA would be subject to a pressure rho gh, because you know this is small width. So all points are practically at a depth h below the free surface on this dA, right? So what's going to be the pressure at all points on this at a depth h? Pressure at all points at a depth h is going to be rho gh, right? The force on this element dA, which will act like this, you realize? The force will always act normal to the surface. Force, because of the pressure, will always act normal to the surface, right? So the force acting here, dF, which is normal to the surface, which is now from this way, it's acting like this, right, is going to be rho gh into dA. Yes or no? The total force on the surface, and all these forces, all the dFs, are normal to this plane surface. They are in the same direction. That means I can perform an ordinary summation of all these dFs. All the dFs are in the same direction. They are normal to the surface. When you see from here, they are in this direction. Yes or no? Right? So the net force normal to the surface, F, will be sum of all the dFs, where h runs from h1 to h2. H runs from h1 to h2. Yes or no? Does it make sense? Now, assuming rho to be independent of h. If they tell you rho is a function of h, then plug in rho as a function of h. Right? There could be fluids in which there could be a variable rho, continuously variable rho. But let's talk of a simpler situation where rho is constant. So if rho is constant, then rho ng will wriggle out of the integration sign. Rho ng will come out of the integration sign. So this will then be rho g integral h dA. H runs from h1 to h2. Yes or no? Integral h dA, where h runs from h1 to h2. Now, I have a remark here. This element that I've chosen is at a depth h below the free surface. Is at a depth h below the free surface, right? This is dA, right? Its mass will be proportional to dA. Its mass dm would be, say, some constant times the area dA, right? Right? This lambda will remain the same because thickness is the same, right? The total mass of this surface would be the total area, this total area A into lambda, Yes or no? Now, if I had to compute the depth of the center of gravity of this surface, depth of the center of gravity of the surface, that means what would I do? I'll take, that means h bar, which is depth of the center of gravity. H bar is the depth of the center of gravity. Which in this case matches with the center of mass as well, right? That's going to be integral h dm. H runs from h1 to h2 divided by the total mass by definition. That's the depth of the center of gravity by definition. Yes or no? Now dm, the mass of this element is lambda into dA, right? So this is lambda coming out h dA, h1 to h2. Yes or no? Divided by total mass. Total mass would be the total area into lambda. Total mass will be proportional to total area. So lambda into mass into area, total area A. That will give me the position of the center of mass or center of gravity of this vertical surface. Depth of the center of gravity of this vertical surface. Yes or no? Right? Lambda then will be taken care of. That means h bar, the depth of the center of gravity, is integral. See, lambda got cancelled, so let me just remove it. Would be integral h dA. H runs from h1 to h2 divided by the total area A. Yes or no? Does it make sense to all of you? Right? Which means also you can see that integral h dA. I keep selecting various dAs at various depths h and I sum them up from h running from h1 to h2. I end up getting h bar, which is the depth of the center of gravity, h bar, which is the depth of the center of gravity, into the total area A of this planar figure. Yes or no? Which will be A into h bar. Yes or no? So integral h dA, h running from h1 to h2 for this uniform thin lamina, right, is going to be the depth of the center of mass or center of gravity from the free surface of the liquid into the total area A of this immersed or submerged surface. Yes or no? Do you register this? All that has happened is the masses have been replaced by the corresponding areas. dm will be the area element, capital M will be the total area, will be replaced by the total area. Yes or no? H bar is the depth of the center of gravity. H bar is the depth. This is the definition of the center of position of the center of gravity, right? I take a mass element into the depth of that mass element, another mass element into the depth of the center of element. I sum it up and divide by the mass. That will give me the depth of the center of gravity of this submerged surface. H bar is the depth of the center of gravity of the submerged surface. Yes or no? Will mass not be proportional to area? That's it. So dm will be lambda into dA. Mass would be, total mass would be total area into lambda. Right? Mass proportional to area. dm proportional to dA. And the constant of proportionality is lambda. dm would be lambda into dA. Total mass m would be lambda into total area A. Isn't it? Mass will be proportional to area. If thickness is uniform, if this thickness is uniform. But if this thickness varies, then the total mass will not be proportional to total area. If you select mass elements at various points, they will have, if you select area elements at different points, they will have different masses if the thickness was not constant. You know what I'm saying? In any case, we are talking of a uniform thin lamina. Yes, to the surface, always, always. Will be perpendicular to the area element. will be force perpendicular to the area element. This is the area element, it will be perpendicular to the area element. See, right now, I'm assuming that liquid exists only on this side of the surface. If it also existed on this side, then they will cancel off, then net force will be 0, isn't it? See, it's like, why are we studying this? You know, it's because there is a dam, there is a gate, and it is located at the end. This gate will sometimes open, this gate will sometimes close. So we need to know the force acting on this gate. This is a practical engineering situation. We will not unnecessarily immerse surfaces in liquids for the heck of studying forces, right? We need to, right? We would do so at one end, so that, you know, this would be typically like part of a dam kind of a thing. Damn it. Do you understand this or you don't? So do you understand that the depth of the center of gravity would be h dA, h1 to h2, divided by the total area A. So integral h dA would be depth of the center of gravity into the total area A for a uniform thin lamina. How about it? Is there any confusion on this? No confusion. Very good. Now, can I remove the clutter from here? So, integral h dA, h running from h1 to h2 would be rho g into h bar, rho g into h bar into A. That means rho g h bar is what? Pressure at a depth equal to the center of gravity. Pressure at the center of gravity into the total area A. Rho g h bar is the pressure at a depth equal to the center of gravity. That means pressure at the center of gravity into the total area A would be the normal force acting on this submerged plane vertical surface. Submerged plane vertical surface. Yes or no? Are you finding it difficult to register? Not at all? So far so good. Can I wipe this off? Which means now say this is a liquid of density rho, and at one end there is, this is a rectangular surface, say. This is a rectangular surface, and when you see this rectangular surface from here, this is what you'll see. This is what you'll see. You'll see a width B, right? That's going into the plane of the board. B is going into the plane of the board. This is this view. So B is going into the plane of the board, and this is like this thick, which is reflected here, right? Right? And D is the depth, right? The other dimension of this rectangular uniform lamina. Clear? And if I want to find the total force on this, okay, now let me assume that the upper end is at a depth h0. The upper end is at a depth h0 below the free surface. I want to find the total force acting on this. All that I need to do is I need to locate the center of gravity of this with respect to the free surface. So the center of gravity would be d by 2 units from here, right? This is the center of gravity, which will be located here, right? And this will be d by 2 units from this, yes or no? Right? That means the total depth of the center of gravity is what? H bar is going to be h0 plus d by 2 is the depth of the center of gravity. From the free surface, h0 plus d by 2 is the depth of the center of gravity of this plane vertical surface, yes or no? Right? So the total force acting on it would be rho g into h bar, that's the pressure at the center of gravity, rho g into h bar, which is h0 plus d by 2 into the area A. Area A is B into D. Area A is B into D. total area A is B into D of this rectangular surface. Yes or no? So all that you need to do is locate the center of gravity of this plane vertical surface and the depth of this. Calculate the pressure at this point, at this depth, which is rho g h bar, right? And then into the total area will give you the total force on this submerged surface. Confusion, eh? Seems good, right? I could have had, say, a triangular lamina. This is a rectangular lamina. Let's look at what happens if the lamina is triangular, right? Let's see what happens when the lamina is triangular. Can I wipe this off? Clear now? Okay, suppose I have, instead of this, I had, say, when you see from here, you see a triangle, say. When you see from here, let's say you see a triangle. And say it's an inverted triangle, say. This is an inverted triangle, right? That's the surface you're seeing. When you see from here, you see an inverted triangle. That's a plane surface, uniform lamina. And say B is the base length of this triangle, right? And this base is parallel to the free surface. This base is parallel to the free surface, right? And h is the height of this triangle. From this vertex to this base, that's the height of this triangle, right? And I want to find the force on this triangular lamina. I want to find the force on this triangular lamina. So all that I need to do is, I need to first locate the center of gravity of this triangular lamina. I need to locate the center of gravity of this triangular lamina, right? So if G is the center of gravity of the triangular lamina, then would you want to believe that this G would be at a depth h by 3 from the base and 2h by 3 from the vertex? It would be h by 3 from the base and 2h by 3 from the vertex? Yes or no? So then, what's the pressure at G? The pressure at G is going to be rho G into depth of G. What's the depth of G? h naught plus h by 3. That's the pressure at the center of gravity into the total area, B into H. Total area, half B into H. Total area A is half BH, base into altitude. That's the net force acting on this triangular lamina. That's the net force acting on this triangular lamina. Rho G H naught plus H by 3 into half BH. If it was inverted, then this would have become 2h by 3. This would have become h naught plus 2h by 3 if you invert it, because this length is going to be 2h by 3. If you invert it, that is what you will get. You know? So far so good. Suppose I have a circular lamina. The gate is circular. These are actually gates. In hydrostatic terminology, they are called gates. Parts of dams, right? Suppose I have a circular lamina. Can I wipe this off? Right. Fairly simple. So which means the whole thing is having knowledge of position of center of gravity of various entities, various geometries, laminar figures, right? So suppose now this was circular, and if it was circular, then you view from here, this is what you'll see. This is what you'll see. Yes or no? Now if it's uniform circular, suppose the diameter of the circle is D. Then the center of the circle will be the center of gravity, right? Will be G. And this you can see would be the radius R. radius r of the circle, right? So again, what would be the force on this? Rho g into depth of center of gravity, which is h naught plus r, into the area of the circle, which is pi r square. Area of the circle, which is pi r square. That's the force acting on this normally. Let me make it a little more involved. Suppose instead of a circular lamina, you had a trapezoidal lamina. You had a trapezoidal lamina whose cross section is a trapezium. Whose cross section is a trapezium. All right. Suppose I had something like this. The cross section is, that means when you see from here, what you see is a trapezium like this. What you see is a trapezium of this being A, this being B. These are the parallel sides A and B, and say H is the separation between A and B. H is the separation between A and B. Okay. Now, I want to be able to locate, let's say, this is the center of gravity somewhere here. This is the center of gravity somewhere here. All right. I want to locate the depth of the center of gravity. I want to locate the depth of the center of gravity. Clear? I want to locate the depth of the center of gravity. Clear? Now, how do I find the center of gravity of this? So you know, it will be a revision for us. It will be a revision for us in as far as computation of center of mass is concerned. So you know, center of gravity becomes synonymous with center of mass in this case. How do I do this? How does one do this? What we do is, I break this trapezium into two triangles. All right. I break this trapezium into two triangles. Say the center of gravity lies somewhere here of the whole thing, right? And the center of gravity, say, is at a depth x below this A. X below this A. Center of gravity is at a depth x below this side A. Okay. So now look at these two triangles. This is one triangle, the shaded triangle, and this is the dotted triangle. This is the dotted triangle, right? Now, to compute the center of gravity, what do? Summation mixi by summation mi. The masses can be replaced by areas because masses are proportional to areas, right? So, to compute the depth of the center of gravity from A, what I'll have to do is look at this triangle, compute the depth of the center of gravity of this triangle from A, look at this triangle, compute the depth of the center of gravity from A of this triangle, then A1 into H1, the depth of center of gravity, plus A2 into H2 divided by A1 plus A2. Yes or no? So for the shaded triangle, for example, for the shaded triangle, would you want to believe that this is of a height h, isn't it? This is of a height h. its center of gravity the center of gravity G1 of this, the center of gravity G1 of this would be at a depth 2h by 3 from the vertex, 2h by 3 from the vertex, because this total height is h. So from this vertex it's going to be 2h by 3, right? What's the area of this? Half of b into h. So for this triangle G1, that is, in order to locate G1, the depth of the center of gravity of this triangle from A, side A. This is side A, this is side B. What would I do? Well, A1, what's the area A1 of this? Half of B into H. Right? What is the depth H1 from the free surface? 2h by 3. Right? Now, look at G2. The center of gravity of this triangle is at G2, say. Now, from the base, it's going to be h by 3 units. Its area is going to be half of A into H. This triangle has area, half of A into H. Half of A into H, right? And its H2 from A is going to be H by 3. H2 is going to be H by 3. Yes or no? Right? So, the position of the center of gravity, x, from this is going to be given by what? X would be A1 H1 plus A2 H2 by A1 plus A2. You can obtain the depth from the side A of the center of gravity of this trapezoidal lamina. Yes or no? Do you all understand whatever I'm saying here? You know? This was my H1, 2h by 3. This would be H2, which is h by 3. And then the depth of G, which is x, would be A1 into depth of the center of gravity of this plus A2 into depth of center of gravity of this from the side A divided by the total areas. That will give me the depth of the center of gravity. From side A, yes or no? So which means from the free surface, the depth from the free surface of the center of gravity of this would be what? Would be h naught plus x. Yes or no? H naught plus x would be the depth of the center of gravity from the free surface, which is going to be h naught plus x that we have computed here. Right now? Therefore, the force acting on this is going to be rho g into h bar. Rho g into h bar, that's going to be the pressure at the center of gravity. Rho g into h bar is the pressure at the center of gravity into the total area. Total area would be average of parallel sides into distance between them. Average of parallel sides into distance between them, h. That's what you do for a trapezoidal lamina. Yes or no? Clear now? How do you compute the force at this on the lamina? Pressure at the center of gravity, which is rho g into h bar, into the total area. Total area is average of parallel sides into distance between them, a by 2 into h. Right? Area for trapezium. Average of parallel sides into distance between them. Yes or no? One thing at a time. They may not be laminar. It could be like, it does not matter. It will not matter because eventually, you know, this is like a gate. The dam, this is part of the dam. This is not the dam. This is part of the dam which could be like a gate which will open and close when required. Right? So I'm not ignoring what you're saying, but I'm saying we are looking at simpler elementary situations. Right? Can I wipe this off? Now, so this gives us a fair deal of an idea on what to do if we have a plane vertical surface of different kinds of geometries, immersed or submerged in a fluid of constant rho at rest. Right? But that's not enough. Why is that not enough? See, when these designers go on to design these gates, let's say this is the free surface of a liquid and there is a gate here. I know how to calculate the force on this gate, right? In order to calculate the force on this gate, I said, all right, it's going to be rho g into the depth from the free surface of the center of gravity into the total area, right? What really happens is, so that's a hydrostatic pressure, that's a hydrostatic force, F acting on it. I have to hold this gate in equilibrium, isn't it? I have to hold this gate in equilibrium. If I don't hold it in equilibrium, what will this force do? This force F will accelerate the gate to the right. Yes or no? Yes. You don't want that to happen, right? So which means there must be a mechanical means which will exert an equal and opposite force. That will exert an equal and opposite force on the gate in this direction. That will maintain translational equilibrium. But the problem is, it is not just translational equilibrium, I also want rotational equilibrium for the gate. Because if the hydrostatic force is like this, and my mechanical system exerts on this a force F like this, it will maintain translational equilibrium, but it will rotate. There will be a non-zero torque acting on this. There is going to be a non-zero torque acting on this. Yes or no? So which means it is not enough to know F. To maintain equilibrium of this gate, it is not enough to know F. I should also know where this entire force could be imagined to be acting. From a rotational perspective, I should know that the entire force acting, see, after all, on this submerged surface, you know, on this was my submerged surface, PQ. And this was my, say, pressure diagram. Pressure increased linearly from P to Q. Pressure increased linearly from P to Q. This is what happened. This is my pressure diagram. Yes or no? And because of this pressure variation, there is a net force F that acts on it. I want to figure out a certain point, say C. On this surface, I want to figure out a certain point C where I could imagine this entire force F to be acting. Because if I figure out a certain point C where I could imagine this entire force to be acting, then I can apply my externally applied force F at the same point, in an opposite direction. Then what would happen is these two forces will not only produce translational equilibrium, will also produce rotational equilibrium. Yes or no? Right? Now, the point where I can replace this entire force to be acting, I call that as the center of pressure. Right? This point C, where I can replace the entire hydrostatic force acting on the plane lamina, vertical lamina, this is the center of pressure. This is the center of pressure. You know what I'm saying? So I should know not only the total force acting. I figured out it's so easy to compute the total force acting on this lamina, right? Pressure at the center of gravity into the total area will give me the force acting on this lamina, right? But I need to find a unique point C on this lamina where I can imagine this entire force to be acting, right? And this point C is called the center of pressure. So from the point of view of designers who want to maintain this gate in equilibrium, knowledge of F is not enough. I also want to know the point at which equivalently I can imagine this force F to be acting, which is the center of pressure. Let's then figure out modalities for obtaining the center of pressure for this plane surface. Are you all clear about whatever I am saying? Is there any confusion so far? Naina? Now, look, when you see from here, this will look like, say, some area A. It will look like some area A, right? The center of pressure, let's say, is at a depth hc from the free surface. Is at a depth hc from this free surface. Is at a depth hc from this free surface. Now, so I essentially want a way to compute this hc. Position of depth of the center of pressure, where I can imagine that entire force F to be equivalently acting. Right? The point of application of this force is important. Right? Now, again, if you think about it, if I look at a depth h below the free surface, and this area element dA below the free surface, h units below the free surface. Think about this. Area element dA, h units below the free surface. Then, what's the force acting on this? The force acting on this chosen element is going to be rho GH into dA. Rho GH into dA, right? Now this force F, dF, will produce a turning effect. This force dF will produce a turning effect about the free surface. Yes or no? There is a moment of this dF about this free surface. There is a moment of this dF. There is a torque of this dF about the free surface. What is that torque? dF into h. dF into h would be the moment of this dF about the free surface. Yes or no? Yes. So the moment of this about the free surface is going to be what? dF into h is the moment. Right? If I want to compute the total moment about the free surface, so this is the moment. Because of this dF, about the free surface, if I want to compute the total moment about the free surface, then I will have to sum it up. This is the total moment. This is the total moment about the free surface. Let me call it OO. OO is the free surface. OO is the free surface. This is the total moment where H runs from H1 to H2. Say this was my H1 like before, and this lower end was at a depth H2 from the free surface. H runs from H1 to H2. Yes or no? H runs from H1 to H2. That's the total moment of the force because of hydrostatic pressure about the free surface. Are you confused? No. This dF I can replace by rho g h dA. This dF I can replace by rho g h dA. So the total torque about the free surface is going to be integral dF to be replaced by rho g h dA into H. This was the force dF into H. That's the moment about where H runs from H1 to H2. That's the total moment. And in this case, if this was the direction of the force, then about this free surface, for example, for the shown figure, the torque would be anti-clockwise. The torque would be anti-clockwise. Yes or no? Realize again, rho g will come out. Rho g comes out. Integral h squared dA. H runs from H1 to H2. H runs from H1 to H2. Yes or no? Which means the total torque of all the forces dF, hydrostatic forces dF, about the free surface is given by rho g integral h squared dA. H runs from H1 to H2. H is the depth of various dAs, starting from H equal to H1 to H equal to H2. Is it bothersome? Don't lose clarity in the midst of algebra. Don't lose physics in the midst of algebra. But is this clear or not? Now, reason I computed the torque of all the forces is because now I was looking at a rotational aspect of it. Now the torque of all the forces about the free surface should be the torque of F about the free surface. That's when this F would be considered equivalent, yes or no? Right? So this is the torque of all the forces acting on the submerged surface about the free surface. And that must be the same as the torque of F about the free surface. That means that must be equal to the torque of F about the free surface would be F into HC. F into HC. Yes or no? F into HC. What is F? F is rho g h bar into A. Rho g h bar into A. into HC. Into HC. F is rho g h bar into A into HC. That's the torque of F. So this then could be used to compute HC, because h bar I can either obtain or I will have knowledge of depending on the geometry. So h bar is the depth of the center of gravity of this free surface. If G is the center of gravity of this free surface, if G is the center of gravity of this free surface, h bar is the depth of the center of gravity. H bar is the depth of the center of gravity from the free surface. G is the total torque because of constituent forces will be the torque of F about the free surface. F is the sum of all those forces, right? So I want to find out where I should, instead of taking all these dFs, if I have a total force F, where should this F be acting? so that the torque this F produces about HC is the same as the torque that all these DFs that constituted F were producing about the free surface. See, again repeat, don't get confused. All that I'm saying is, these various DFs acting on this submerged surface will produce a torque about the free surface, right? Now this total F force F, which is sum of all these DFs, I want to apply it at a certain point. I want to apply it at a certain point C on the submerged surface, so that the torque produced by F about the free surface is the same as the torque produced by various DFs about the free surface. So that will give me a reason to apply F at a certain point C. You know what I'm saying? So that's the definition of center of pressure. That means to compute the total torque, either I can take the torques of all the DFs about the free surface, or if I know the center of pressure, then I apply in one shot the force F at the center of pressure, then the depth, then the torque that this F produces about the free surface would be the total torque, hydrostatic torque acting on the submerged surface, right? So that's when I say HC is the equivalent depth where I can imagine the entire F to be acting. HC is the equivalent depth where I can imagine the entire F force to be acting. No, no, of course not. That's the gravitational forces, not hydrostatic forces. Center of gravity will give you the gravitational. I had never said that the entire force was acting at the center of gravity F. All that I was saying was the force could be computed by computing the pressure at the center of gravity into the area A. All that I said was, to compute the total hydrostatic pressure, what we have obtained categorically is, hey, compute the pressure at the center of gravity into area A. It doesn't mean that the entire force was acting at the center of gravity. It didn't mean that. It only meant that to compute the total force, one could imagine the pressure at the center of gravity into the total area A. That will give me the total force. It didn't mean that this force was acting through the center of gravity. Got me, na? There is no confusion on this? Okay. Now, so far so good, right? All's good so far. So, one thing, from this rho g will get cancelled, right? So HC, which is what we are trying to compute, the depth of the center of pressure, where we can imagine this entire force to be acting, where we can imagine this entire hydrostatic force to be acting, is integral h squared dA. H runs from H1 to H2 divided by AH bar. H bar is the depth of the center of gravity. H bar is the depth of the center of gravity. Now, I'm going to cause a little more anxiety to you. But I'm actually essentially trying, in the process of creating anxiety, I'm trying to create very simplified versions of things which you can readily use. Okay. But there is no confusion. This result will give you the depth of the center of pressure. That means this entire force F acting on this lamina, computed from this result, could be imagined to be acting at C. So now if I know that this entire force is effectively acting at C, then to maintain it in equilibrium, I'll have to apply an external force F in the opposite direction, passing through C. Then it will not only be in translational equilibrium, it will also be in rotational equilibrium, because this F and this F will produce no net torque. Yes or no? Okay. Now I'm going to go back to moment of inertia. You remember how we computed moment of inertia? Can I remove the clutter from you? Hey. say the same surface seen from here. I want to compute the moment of inertia about OO, which is the free surface of this submerged surface. Moment of inertia of this submerged surface about this free surface. Right? This is a mass element that I have chosen. This is a mass element that I have chosen. This is the depth h. Then the depth, then the moment of inertia about this OO, moment of inertia of mass. Let me call this moment of inertia of mass. Right? Now let's be more specific. You wonder what else moment of inertia could be. The moment of inertia that you have used and known is moment of inertia of mass. Right? Moment of inertia of the various mass elements that constitute this about OO is going to be what? dm, take a mass element, about this axis into h squared, sum it up, where h runs from h1 to h2. That's the moment of inertia of the mass elements about OO. Moment of inertia of mass about OO, right? Of mass about OO. Of this submerged surface, Right? Clear, na? Now, I'm going to, this mass element has area dA, as you have seen, right? This mass element has area dA, Now I define moment of inertia of areas. If this dm is replaced by dAs, then that will give me moment of inertia of area about OO. You know what? If I replace this mass element by the area element, then I'll, instead of getting moment of inertia of mass about OO, I'll get moment of inertia of area about OO, right? Of area, moment of inertia, right? If ye to moment of inertia of mass, because there are mass elements involved here. I take every mass element, square of its distance from the axis, right? But if I want to compute moment of inertia of area, then replace this mass elements by area elements. That means this dm would be replaced by this dA, right? So integral h squared dA, h runs from h1 to h2. Integral h squared dA, h runs from h1 to h2, will give me moment of inertia of area about OO, will give me moment of inertia of area about OO. OO is the free surface. OO is the free surface, right? This is like IOO, moment of inertia of area. Instead of mass elements, you have area elements. That's all, right? Huh? How's the area distributed? Right? It'll give me an idea of distribution of areas, isn't it? In fact, it will also give me distribution of mass, because areas will be proportional to masses, right? Yes or no? So mathematically, moment of inertia of mass and moment of inertia of area, they have similar looks. They have similar looks, right? Except dm, you have dAs. Yes or no? So in this case, this computation gives me what? Moment of inertia of the submerged surface, moment of inertia of area of the submerged surface about the free surface, about the free surface OO. This is what I get. Right now? Now, which means, you know, the parallel axis theorem, perpendicular axis theorem that holds good for masses will hold good for areas as well. You know, we have read moment of inertia of masses and the two theorems, the parallel axis theorem and perpendicular axis theorem. Except that instead of masses we'll use areas. Instead of masses we'll use areas. Right? Now, look. So let me come down to this now, because this is what is of importance. This is what? Moment of inertia of area about the free surface. Moment of inertia of area about the free surface of this submerged surface. Right? So this is IOO divided by A H bar. IOO divided by A H bar. So this was my submerged surface, this view. This is my OO. This is the center of gravity. This is the center of gravity, which is located at a depth h bar from the free surface. Which is located at a depth h bar from the free surface. Now. So distance between these two axes is h bar. Distance between these two axes is h bar. This is an axis passing through the center of gravity. This is a parallel axis. This is a parallel axis. This is the axis passing through the center of gravity, and this is a parallel axis. There is a moment of inertia about an axis passing through G, IG, and there is a moment of inertia about this axis of the area. Now about the area. So if I am saying moment of inertia, I am talking of moment of inertia of area. Alright. So there is a moment of inertia about an axis passing through G and parallel to this axis. Now can I apply parallel axis theorem to this? For parallel axis, again, masses to be replaced by areas. So can I say I about OO will be I about G A H bar squared. A H bar squared. A H bar squared. I about the free surface is the same as I about an axis passing through G plus area of this. A is the total area of this into square of the distance between these two axes, which is H bar. Which is H bar. Yes or no? That's parallel axis theorem. IG is what? IG is the moment of inertia of the area about an axis passing through G but parallel to the free surface. IG is what? Moment of inertia of area of an axis passing through G and parallel to the free surface. That is IG. Yes or no? That's IG. Clear? Now, I'm going to apply parallel axis theorem to this. This I00, I'm going to replace by I about a parallel axis passing through G plus A H bar squared. A H bar squared. I'll do that. Have I got you muddled? Nahi na? So, HC, which is my point of interest, depth of the center of pressure. I00 to be replaced by IG plus AH bar squared. I00 from parallel axis theorem is going to be IG, I about a parallel axis passing through G plus A H bar squared divided by AH bar. That will give me the depth of the center of pressure from the free surface. Depth of the center of pressure from the free surface. Parallel axis theorem. I about G by AH bar. I about G by AH bar plus H bar, which is clearly greater than H bar, which is clearly greater than H bar. That means the center of pressure will be deeper than center of gravity. The center of pressure, depth of the center of pressure would be more than the depth of center of gravity. That means if G lies here, then the center of pressure will be lower than G. Center of pressure will be lower than G. Yes, you're right. You're right. The depth of the center of pressure is more than the depth of the center of gravity. Is it getting burdensome, or are you there with me on this so far? Huh? Because I'm not done. So, second, realize the depth of the center of pressure does not depend on the density of the liquid. Depth of the center of pressure, see, rho had earlier got cancelled. It does not depend on the center of gravity of the liquid. I'm sorry, it does not depend on the density of the liquid. Kaan pakda bhai. It does not depend on the density of the liquid. Center of pressure does not depend on the density of the liquid. Right? And it will be deeper than the center of gravity. It will be deeper than the center of gravity and will be independent of the density of the liquid. Right, Aditya? Now, so it then becomes important for us to compute IG for some regular geometries. Moment of inertia of areas for some regular geometries I must be able to compute. IG, moment of inertia of area about an axis passing through G and parallel to the free surface. I must know that, because that I am going to use in this result, center of pressure result. Chalo dekhi, let's see. Can I wipe this off and do some basic calculations of IGs for some regular stuff? Say free surface and there was a rectangular lamina. Rectangular lamina. This is when you see from here. This is an axis. This is the base B, and this is the length D. So we are calculating IG. IG means what? I choose an axis passing through G and parallel to the free surface, therefore parallel to B. In this case, this axis will be parallel to the base B, right? So I want to find about this axis. This is my axis about which I want to find IG. What I do is, to find IG, I take at a distance x a strip of width dx, a strip of width dx. What will be the area of the strip? P into dx will be the area of the strip. What is its distance from this proposed axis? X. So x squared into b dx, x squared into area element will be the contribution to IG made by this strip, contribution to ID G made by this strip, right? And I want to sum it up to calculate, to include all the strips. This point would be x equal to minus d by 2 and this will be x equal to plus d by 2. What do you say? This is x equal to 0. This will be x equal to plus d by 2, this will be x equal to minus d by 2. So the total would be minus d by 2 comma d by 2, that is I about G. Yes or no? Or you confused kya? Area element into square of the distance from the axis. Area element is b dx. This is width b, thickness dx. into square of the distance from the axis about which we are computing the moment of inertia, right? If you integrate this, this would be x cube by 3. So b by 3 x cube, where x runs from minus d by 2 to plus d by 2. D cube by 8, 2 into d cube by 8, d cube by 4. So this is 1/12 bd cube. 1/12 bd cube. I about an axis passing through G and parallel to the base. This is I about an axis passing through G and parallel to the base. Tough kya? Nahi na? Hey, what would be I about this axis? Say this is mm. I about mm would be I about G plus area B into D into d by 2 squared. Four, 3 and 1, 4, bd cube by 3, is it? Bd cube by 4, 1 by 4 plus 1 by 12, 3 by 4, 1 by 1/3 bd cube. You know? About it. But what would be the depth of the center of pressure? Depth of the center of pressure would be G by AH bar plus H bar, where IG is computed about an axis parallel to the free surface passing through G. Acha, what is H bar for this? Suppose this was H naught. What would be H bar? H naught plus D by 2. Right. H naught, H bar would be H naught plus D by 2. Area we know is B into D. Right. IG is 1/12 bd cube. So you can compute the depth of the center of pressure for this. You can compute the depth of the center of pressure for this. Yes or no? Clear? I mean, this you have to remember. IG is 1/12 bd cube. B is the base parallel to the free surface. B is the base parallel to the free surface. D is the other dimension of this rectangle. D is the other dimension of this rectangle. Clear? Clear, no? Circular lamina of diameter D. Circular lamina of diameter D. I want to compute moment of inertia about A, about this axis. To compute moment of inertia of the area about this axis. I want to do that about this axis. Hey, what I do is, and listen to me, that means about a diameter, I want to compute the moment of inertia about a diameter. About a diameter is what I want to compute. What I do is, let me compute moment of inertia of area about an axis passing through G but perpendicular to the diameter, perpendicular to the plane of the lamina. Let me compute this. Moment of inertia about this. What I do is, suppose I take a small strip of radius r and of thickness dr. Now all points on this strip are at the same distance r from the axis passing through G and perpendicular to the plane. So what's the contribution of this area about this axis? Is going to be, first of all, r square into area which is 2 pi r dr. Area of this shaded region is going to be 2 pi r dr, isn't it? Kya? Nahi. Are you losing track? R square into area element. All these points are at the same distance r. So r squared into area element. Area element is what? Circumference of this is 2 pi r into thickness dr. That's the area, isn't it? Circumference 2 pi r into thickness dr. The total moment of inertia is going to be where r runs from 0 to d by 2. R runs from 0 to d by 2. This is about which axis? This is about an axis passing through G, but perpendicular to a diameter, but perpendicular to the diameter, isn't it? About this axis, because all these r's are distances from this axis, right? So what does this turn out to be? 2 pi, this is r cube, so r to power 4 by 4, r runs from 0 to d by 2. This is pi d to power 4, so by 16, 64, 32. Pi d to power 4 by 32 about this axis, okay. But I want to compute I about G parallel, I passing through G along a diameter, I want to compute not about this axis, because this will be parallel to the free surface, right? So my gate is like this. This is my gate, right? And this view of this gate is a circle. This is G. This is the free surface, right? So I would have to compute I about an axis passing through G to compute center of pressure, IG. But that axis has to be, this has to be parallel to this, right? Now about an axis passing through G along a diameter, because this diameter will be parallel to this. ये compute करना है ना, पर ये क्या है? ये तो वो नहीं है. This is this axis, because all distances are taken, r's are taken from this, right? This is not the IG that I need. This is I about an axis passing through G and perpendicular to the circular lamina. Passing through G and perpendicular to the circular lamina. This is what I have, right? So this I know is pi d to power 4 by 32. Now, look, this is my circular lamina. These are, take two perpendicular diameters. Then from symmetry, if I is the moment of inertia about this diameter, then I must be the moment of inertia about this diameter. These are two perpendicular diameters. Yes or no? कोई फर्क नहीं होगा ना? हाँ, about any diameter it's going to be the same, right? So then 2i will be this. Perpendicular axis area, I about this plus I about this will be I about this. Perpendicular axis theorem, I about this plus I about another perpendicular would be I about this. But I about this, so that means I plus I 2I must be I about this. But I about this we have computed is pi d to power 4 by 32. So I about a diameter passing through G, I about a diameter passing through G is going to be pi d to power 4 by 64. Pi d to power 4 by 64. D is the diameter of the from perpendicular axis theorem. Nahi kya? Right now? So essentially then, if this was my circular strip, circular lamina immersed, and say at a depth, the upper surface was at a depth h naught, right? First of all, what would be the force on this? The force on this would be, the net force acting on this is going to be rho g into h bar. H bar would be h naught plus d by 2, right? H naught plus d by 2. This is d by 2. It will act like this, right? Into pi d squared by 4, the area. Pi d squared by 4 is the area. That's the total force. And this force could be imagined to be acting at a depth hc from the free surface, which is the center of pressure. And how does one compute this? This is G, this is G. C will be lower than, this C will be lower than G, right? So HC would be what? I about G divided by AH bar plus H bar. What is I about G? Pi d to power 4 by 64. Pi d to power 4 by 64. We've computed that earlier. I about a diameter is pi d to power 4 by 64 is what we computed, right? So this is pi d to power 4 by 64 divided by area A, which is pi d squared by 4 into h bar. What is h bar? H bar is going to be h naught plus d by 2. Plus h naught plus d by 2. Clear? Can I wipe this off? Another result which I am not going to establish, but say if there was a triangular lamina, triangle base B and height h, right? G is the center of gravity of this, which will be 2h by 3 from the vertex and h by 3 from the base. It will be closer to the base, right? You know about this. And I about G parallel to the base, I about G, this is I about an axis passing through G but parallel to the base B, let me tell you, is going to be BH cube by 36. BH cube by 36, you may want to remember this result. BH cube by 36. I about an axis passing through G and parallel to the base is going to be BH cube by 36. Then from here, how will that change? IG, will that change? How will IG change? IG will not change. HC will change, but IG will not change. Right? हाँ? He asked me, ये triangle को गुरु उल्टा दिया, तो इसका IG थोड़ी बदलेगा यार. IG थोड़ी HC बदल जाएगा, पर IG नहीं बदलेगा. Yes, IG is independent. It has nothing to do with how I have submerged the surface. है ना? वो तो body, right? वो तो body पर depend करता है खाली. Does not depend on how I have submerged it. Geometry, absolutely, only the geometry and nothing else. Stand by. So this was a surface that was positioned vertically. Plane surface positioned vertically. But that surface could have been positioned inclined with respect to the horizontal. Could have been submerged inclined with respect to the vertical, not along the vertical. If this is the free surface, this is the submerged surface. This is the submerged surface. This is the submerged surface, submerged plane surface at an angle theta with respect to the free surface. This is the free surface. This is the submerged plane surface at an angle theta with respect to the horizontal. The surface could have been like this, say. Right? Now, again, you know, I'm not going to, G is the center of gravity, which, you know, when you see from here, this G is located somewhere here. You see this view is this, right? And the center of gravity is at a depth h bar. The center of gravity is at a depth h bar. Once again, let me tell you, even when it is inclined, the total force F, no, total force, because of, see, this is a liquid, this is the liquid of density rho. The total force will still be normal to the surface. It will act at the center of pressure C. It will act through the center of pressure C. And to compute the magnitude of the force, again, all that you need to do is once again locate the center of gravity of the depth of the center of gravity of the free surface, depth of the center of gravity of the free surface, compute the pressure at that point, rho g h bar, and that into the total area A, that into the total area A will give me the total force F acting. And the depth of the center of pressure is HC. The depth where you can imagine the entire force to be acting, the depth of the center of pressure is FC. Now this is the direction of the submerged surface. This is perpendicular to this. This is a line perpendicular to the direction of the submerged surface. This is where the submerged surface is. This is the direction perpendicular to that. Let me tell you the final result. The depth of the center of pressure for this inclined surface. Depth of the center of pressure of this inclined surface is going to be IG. Now, what is IG? IG is moment of inertia about an axis passing through G, matlab isme, about this, parallel to this line, parallel to, this is OO, this is OO, passing through G, and parallel to OO. I about an axis passing through G and parallel to OO, this OO, if you view from here, right? IG divided by AH bar sine square theta. See, if you put theta equal to 90 degrees, you get a vertical surface, and it reduces to the previous situation, isn't it? Plus H bar. IG by AH bar sine square theta plus H bar. I'm not getting into the derivation of this, but it's very similar. There's no rocket science in it. Theta equal to 90 degrees will reduce it to a vertical surface, right? H bar is the depth of the center of gravity from the free surface, right? मतलब सोचो कि suppose this is a rectangular surface, when you and say the top end is 1 meter below the free surface, when you view from here, say this is the rectangle that you see, and this rectangle is say 5 meters going into the plane of the board and 6 meters like this, 6 meters like this. So very clearly 6 meters like this means what? Means you will have to go like 3 meters from here, 3 meters from here to locate the center of gravity, 3 meters from here to locate the center of gravity. Yes or no? You will have to go 3 meters from here to locate the center of gravity, right? Now this angle is theta. So this will be like a 3 sine theta. This will be like a 3 sine theta. Right. 3 sine theta. And this is 1 unit. So H bar is going to be 1 plus 3 sine theta in this case, for example. नहीं क्या? Clear, no? देखो बेटा, when you view from here, you see a rectangle. This is 6 meters. So halfway down, you locate the center of gravity G here, 3 meters. So this is 3 meters. Now this angle is theta. This is also theta. So this length is going to be 3 sine theta plus 1. That's the depth of the center of gravity. 1 meter plus 3 sine theta. That's the depth of the center of gravity. Clear? Now, can I wipe this off? So far so good. Yes. देखो, again, think about it. Okay, perpendicular component never दरकार नहीं. Think about it. This is my surface, okay? PQ. And say this is the view. This view of this surface is this, okay? इबार देखो, what I do is at a depth h, I select an area element. That means when I view from here, that area element is my dA like this. right? Now, the force acting on this dA, do you realize, will be like this? Perpendicular to the surface. That will be the force acting on this dA. Perpendicular, right? This way, that is, when you see from here, this way. So now, what's the pressure at every dA? Rho GH, right? Because all these dAs are at the same depth. That means this dA is a strip like this coming out of the plane, right? Nahi kya? So what's the force on this? Rho GH into dA, right? And all perpendicular, all forces at every dA is perpendicular. So I can add these forces, and this depth is H1 and this depth is H2, right? The total force will be sum of all of this, where H runs from H1 to H2. Now, if I take rho G common, then integral H dA, H1 to H2. Hey, what is the depth of the center of gravity? Would be integral H dA divided by total area A. H runs from H1 to H2. That will be the depth of the center of gravity. That means integral H dA H1 to H2 would be A H bar, which is the depth of the center of gravity. So this is rho G A into H bar. Integral H dA H1 to H2 is A into H bar. Yes or no? So which is like rho G into H bar, which is the pressure at the center of gravity, into area. Right? It didn't matter whether it was inclined or not. Got me? Stand by.